Oh, hello everybody. Welcome to our virtual IDIG presentation this year in really crazy times. And our title for this contribution is Prediction of Limit Strains during Non-Proportional Load Path with a Change in Loading Direction. And this is what you will see a really important additional point which should be taken into account for an accurate prediction of limit strains in sheet metal forming. The agenda is as follows. We will start in the usual way with the introduction and motivation, and then our content presented in several steps. Let's start with the introduction and motivation. All we know, forming limit prediction is one of the major tasks in simulation of sheet metal forming processes. And in addition to proportional loading, also non-proportional load path influences the formability of the material significantly. We know that the linear FLD is, especially for non-proportional load path, not valid. And so far, many different models exist to overcome this problem. So we have a set of models, and which was proven also for parts which are produced in real industrial applications like door inner or other parts. Now, as we all know, especially for the experimental prediction, it's not easy for these non-proportional load paths to have a suitable set of tests on test equipment. Therefore, we have designed a special tool at our institute, as you can see here, where we can really perform homogeneous forming steps for non-proportional load path. From the dimensions, it's about 1.60 meters to 1.30 meters. And what's the big benefit of such a tool? That you see here, you can realize any desired preforming step just by changing the plank within the same tool. Here we have the small sized one for the uniaxial tension, and then these butterfly shaped specimens for plane strain and multi-axial strain, and the big one for biaxial strains. And with this tool, it was used for our proposed non-proportional load path so far. But here again, what's a big benefit now, that it's also possible to change the loading direction for the second forming step, as you can see in the next slide. So with this special tool, we have a test equipment where we can put out secondary specimens, also with changing in the loading direction. We know that's also from the definition not so easy, so we have chosen clear names. IF means initial forming, and PF means the post-forming step. And the 0 and 0 is always with respect to the rolling direction. So here, this is the one we have also used in the past, where we have two different forming steps, but one in 0 degree and the second one also 0 degree with respect to the rolling direction. With this tool now, it's also possible, from our point, firstly, really in a systematic way, to change the loading direction for the second step. The question is how important it is, but this is the main motivation of this paper. So here we have the option of 0 and 45 degrees and 0 and 90 degrees. Okay, with this tool, now we can perform our secondary tests. You can imagine for such a shape, it's possible to do Nakajima tests. The Nakajima setup you can see here, it's really conventional, one with die plank holder and a spherical punch. So first, we have to analyze the preforming results that we really have a sufficient homogeneity of the preforming step. This was proven with an Aramis or Argo system from GOM. And so we have a preformed area, and important is that it is large enough to do secondary tests. With the measurement in Aramis, you can prove the history, and with Argus, you can prove the final strain distribution. And here you can see that the homogeneity within 80 millimeters is really very, very good. So we can fix at this point, we have a tool where we have the option to do any preforming steps and with a sufficient homogeneity to do secondary tests. Now the hard work begins. That means we are doing many tests, as you see here. So in total 20 tests with a sufficient number of repetitions where we vary the loading direction and also the amount of preforming strains. We know it's also important to differ within the whole map, and then we have chosen the names PB for biaxial strain, PS for plane strain, U for uniaxial, and M for multi-axial, and always the P for pre-strain. So here you see the whole map of experiments of pre-strained specimens and the FLC within 0, 45, and 90 degrees. So now what's coming out? On the left-hand side, you see the combination of 20% preformed and first and second step in 0 degrees with respect to the rolling direction. So the expected and also published result that we have an influence of the angle and the proportion of pre-strain, and we can measure experimentally the remaining formability in the way of an FLC. Also for 50% with respect to the FLC, you see here also from our point the really suitability of the test set up to do these tests. So these experiments were not really surprising, but what's still missing is the influence of changing of the loading direction. All these tests were done in 0-0 combination. And now for us, we expected, due to these different FLCs, which are slightly different, a small difference, and did the test also when changing the loading direction with respect to rolling direction. And first with 25%, and here a little bit happened, but not so much. But now have a look on the right figure. Here, I want to highlight what's coming out. You see the FLC. In blue, you have the 0-0 combination. And in red, you have the 0-90 combination. And what you really see here for the 0-90, also in plane strain and uniaxial strain, we have a big difference. I want to highlight again, the only difference for this test with respect to this and from this to this, that the first one, this direction, and again second step in this direction, and the second one, this direction, and then only in 90 degrees. So all stress-based models definitely can't predict such a behavior because the stress state itself is not changing because it's still uniaxial tension, only that with 0 or with 90 degrees. But the remaining formability and the prediction of limit strains are really a big difference. And when you have a look in this in-between curve, 0-45, interestingly here, for the combination 0 and then plane strain in 45, nearly nothing happened with respect to the 0-0 combination, but with a 0.45 and both in uniaxial direction, the point is also down here. So you can see that we have a kind of two different failure modes, big influence or no influence. And this was analyzed also in detail in our current this year SIRP presentation, which is also available. Just due to the time, only a few words, the hypothesis why this happens, that we have a totally different behavior of damage and microvolts. Due to the texture development, we have an inhomogeneous hardness field, and this leads to the occurring of microvoids when we have a sufficient texture development. For details, please have a look in this paper. Here for the IDDRG, it's important how to go on, because now we definitely have seen this non-proportional load path with respect to different loading directions and rolling directions is a really important topic, and so far totally ignored in our industrial applications and also in the academic ones. And now here for the IDDRG, our important topic is how to bring this idea into a model where we can predict within deep drawing simulation and so on. So what we propose is a phenomenological approach. Of course, it would be really good to have a wide model where we can have this void and nucleation appearance within a model, but this is not so easy. But on the other hand, in our phenomenological description within the framework of this generalized forming limit concept, even when we have lacks in understanding, it's possible to do simulation taking this effect into account when we have a suitable number of experiments. And I hope that you are convinced that we have this suitable amount and which is great enough to do this modeling in the sense of a phenomenological model. Just to summarize how it works, here without the changing loading direction taken into account is our published model, this generalized forming limit concept, purely phenomenological. The typical 5 steps, starting with the experiments, then always what is necessary for a phenomenological model, the parameterization in response space, and then the compilation of a meta model and the generalization for several changes in direction. Therefore, it's really important, what's also necessary for the understanding of the generalization for the effect of change in loading direction with respect to rolling direction, that inside the model, there's only an interpolation scheme. That means here you see it for a point like here. Here in colored bullets, we have the experimental data. And the only thing what we are doing is an interpolation in an intelligent way. Then when we can predict for any point lying in between with the interpolation scheme well known from finite element analysis, what's the remaining formability, or as you can see here in black. And then it's possible to do for a bilinear model the prediction of formability, and with this generalization of the concept of equivalent pre-strain for any arbitrary load path where we have several changes in loading direction. And now the important step is how to bring a third dimension within this model, where we also have the option to change the loading direction with respect to rolling direction. And then it's quite easy, like 2D and 3D simulation. The 2D are pre-strain and post-strain as the first step, second step. And now the 3 dimensions are preforming direction, preforming loading direction with respect to rolling direction, and then on the Z-axis, the strain path length ratio, which means the remaining formability. So you see here, just from a quad to a hex element, it's possible to do these generalization and taking into account the whole available set of data. So here you see a cut for visualization, where you have loading direction, strain path ratio, and strain path length. So this model is now available. We have coded it at our institute for the material, this cold-rolled 340 microalloyed steel. And now, of course, the question is validation. No model without validation, especially when we have a phenomenological model. For validation, we have designed a new tool, also at our institute, which is similar, but in details really different to a Nakajima test. In the Nakajima test, the objective is to have a clear defined strain path to analyze strains in one direction to have a point on the FLC. And we call this material under control test, MUC, of course, a similarity to our city Munich, where we have a really different objective. This tool was designed to have a wide amount of strains and strain distribution, which is not only on one combination, but also on a wide range of different strain angles and strain distributions. And when you can reach this by using this butterfly-shaped blank holder and also a shaped punch, as you can see with here really different to the punch. The big benefit of this test that we still have a locking bead. So lubrication is, of course, let's say a challenge, but not a big challenge, because we don't have a material flow outside the locking bead. And now you see here the tests which were done within this new shape. So we have done the combination initial forming 0, post forming 0, post forming 45, and post forming 90 degrees. And was also what came out, this test, which is more similar to industrial application, that we have different points of failure and also different ways of shear bands which are occurring. So you see here really big change in the maximum height and also in the location where the localized necking is occurring. And now what we did, made the experiments, analyzed the strain, put in the strain in our phenomenological model, and compared the predicted failure with the real failure. And this was done here. So you see here really different points which occurred for the failure, and also from this intersection cut seems to be a good prediction. Now you can analyze it in more detail. Here in blue, our model, and in gray, the experiments. And what we think, what it's really convincing, the high accuracy. I want to highlight again, the tests for calibration of the meter model were done before. And we have chosen a more industrial applicated boundary value problem, and we see that as well as the amount and the location of failure can be predicted accurately with this phenomenological model. So I want to summary and conclude my presentation. So the influence of change in loading direction with respect to rolling direction is investigated. And this change in loading direction significantly influences the remaining formability, and with a suitable amount of tests, it's possible to make use of a phenomenological approach for modeling, which can be used for prediction of any artificial strain distribution within industrial applications. Therefore, thank you very much for your kind attention. Here you see some references, and also I would be happy for an interesting discussion on potentials and also limitations of this proposed method. Thank you very much.